Hi, this is Angela Galloway, and I'm doing Math 146. We're in Unit 4, which is Chapter 12. This is for 12.2. For 12.2, we're going to be talking about measures of central tendency. So what are we talking about with central tendency? Well, if I was to draw, I'll try and draw our data here, okay? So let's say, we've got data that there's a histogram under here, right? And so the general shape of the data looks like this, okay? So, you know, the first thing we kind of do with data is we kind of look at the shape, is it all centered in the middle or over here to the left or the right or whatever. But after that, then most of us want to know, where's the center at? So like, for example, if I was looking at test grades, I want to kind of know where did most people score? Or if you're looking at heights, you might want to know where are most people's heights located at, right? So that is going to be central tendency. That is where is the center of this graph, okay? One way we can figure that out is by calculating the mean, okay? The mean, of course, is also known as the average. So it's going to be the most common measure of central tendency that we'll see used. But we're going to have two means, okay? One mean is the population mean. The other one is the sample mean. So why do we have two means? Well, remember we talked about back in chapter or back in the first part of this chapter, we talked about how we have a population, right? And from the population, we're going to take a sample of a certain size, right? And from that sample, we're going to collect data and calculate some statistic, right? So from the sample, we're going to calculate, let's say, an X bar, okay? That is our sample mean. That is called a statistic. But if I was able to calculate data from the entire population, for example, if I was taking a census or if I was doing something and I wanted to collect data from maybe all students at my college, it might be possible for me to collect all of that data. If I'm doing that, then the mean that I create is called mu, okay? It's the Greek letter M, which we call mu. We say it like that, or that's how it's spelled. So typically when we're talking about parameters, so that means numerical summaries coming from a population, they are generally going to be Greek letters. When we talk about our statistics, they usually are not Greek letters. They're usually lowercase letters or they have some special kind of marking on them, and they're going to be our statistics. Okay, so from the sample, we get a sample mean. From the population, we get a population mean. Now, both of these are actually calculated the same way, and you probably all know how to calculate a mean. You add up all the observations together and divide by your number of observations, right? In this case, we're going to call that N, capital N or lowercase n, and that stands for our sample size. Here, the lowercase n is always our sample size. So how many people did we have in our sample? A capital N just means you're dealing with the population, so it would be called the population size. Okay, so those are our two means. All right, so now let's calculate a mean. Your weekly paychecks from your new job are below. Find your average pay for the last 8 weeks. So this in the formula means that you sum up all the observations, okay? So we add all of these together, we get 3190, divide by 8 because there were 8 different paychecks, and you see that you got $398.75 on average each week, okay? And so that's how we find a mean. Now there's more measures of central tendency, okay? We could use the mean, and that tells us the average. We could also use the median. The median actually shows us where the middle of our data is. So it gives us the middle observation of numbers. So some examples here, we have information on how to calculate the mean, but sometimes it's just easier just to see it in an example, okay? So let's say we have this data set that's 1, 3, and 5. What is the middle number? Well, 3, right? So our median would be 3. What if I had the numbers 1, 4, 8, and 9? Now where's my middle number? Well, there's not actually a middle number, right? The middle would be somewhere in between 4 and 8. So the way we calculate the median is we say it's going to be in the middle of 4 and 8. So we add 4 plus 8, divide by 2, and in that case we get a 6. Okay, so if you have an even number of observations, then your median is going to be in the middle of two numbers. So you would add those two numbers, divide by 2 to find the middle of those. If you have an odd number of observations, then the median is going to be the number that's right in the center. Okay, now notice that to be able to calculate the median, we have to have our data written in order. Okay, so we have to start with the smallest number and go up to the highest number. So if your data is not already in that order, then you need to do that first. Okay, so you do that first, then you find the middle. Now we can use this formula here, the n plus 1 over 2, to calculate which observation is going to be our median, okay? So for example, when this one, if I have 3 data points, I plug in a 3 here, 3 plus 1 over 2, that's 4 over 2, which is 2. So that tells me that the second observation is going to be my median. So I would go up here, 1, 2, this is my second observation, so that's my median, okay? So realize that this formula doesn't tell you what the median is, okay? It just tells you which observation in your list of data is the median. Okay, so that's a little tricky about this formula because we're usually used to our formulas giving us the answer, right? But this formula actually just tells us where to find the median, okay? All right, the next one we can calculate is the mode, okay? It's going to be the simplest to do because you really don't calculate it at all. You just look at your data to find it. The mode is the value that occurs the most often or has the greatest frequency. One of the things about the mode is that it can also be used with qualitative data. So even with qualitative data, you know, you can tell which category occurs the most often, right? And that would be our mode. Now it's possible that your data has no mode. Okay, there could be none of them that are repeated the most, or you could have several things that are repeated the most. Okay, and so you could have multiple modes. So let's look at these examples. Find the modes for the following data sets. Okay, this first set of data, you can see that the 0 is repeated the most often, right? So the 0 is going to be our mode. The next one, none of them are repeated more than any of the others, right? So that would be none. This third one here, 2 is repeated 3 times and 5 is repeated 3 times. Both of those are repeated the most, so 2 and 5 are our modes. For the last one, this is how you would do it with qualitative data. B would be the most often used there, and so B would be our mode. So that's how you do it with qualitative data. Okay, let's do an example to kind of show how we work with means and medians. Let me erase that there. Okay, find the mean and median for the following set of test grades. Would you rather your teacher use the mean or median to calculate your final grade for the class? Okay, typically teachers use the mean, right? They average your grades together. But what we're kind of going to talk about is how sometimes a median might represent your grades better, or maybe the median represents whatever data you have better than what the mean does, okay? And so what we want to try to learn here is how to know if we should use the mean or the median. Because what we want to do is what we did with our graph was we tried to find the graph that best displayed the data, right? We made sure we chose the right graph for our data. We made sure that we didn't use pictograms, that we used correct axes, that, that we didn't make it too cluttered or whatever. We made it easy for whoever was reading it to understand our data. The same thing here. We want to make sure that the statistics we calculate actually accurately reflect our data. Okay, so look at these grades here. We've got 100, 95, 78, 84, 62, and 99. Okay, so find the average of those. So we take the average, add them all together, divide by 7 because there's 7 grades here, and we get an 86.9. Okay, so that would be your mean. Now to find the median, the first thing we have to do is reorder from smallest to largest, because notice these are not in order of smallest to largest, right? So if I reorder these here, now I've got 62 to 100. I've got 7 observations, so to find which one is the median, I would do 7 plus 1 over 2. That gives me 8 over 2, so the 4th observation is the median. So 1, 2, 3, 4. So the 90, okay? So the 90 is the median. So if we were assigning letter grades, based on the mean, you would get a B. Based on the median, you would get an A. So obviously, which one would you rather use? Well, the median, right? But looking at this data, why is the median higher than the mean? Or why is the mean lower than the median? Well, let's look at this data down here when it's in order. Notice that most of your grades were pretty good, right? All these were A's, so you got 4 A's, a B, an almost B, right? So a very high C. And then you had this one test that you just didn't do so good. Now, do you think this test is going to affect the mean more or the median more? Well, we can see from how we calculated these, it affects the mean more, right? Because the mean was lower than the median. But why is that true? Well, notice how we calculate a mean. A mean is equal to the sum of all the observations divided by n. So for the mean, it takes into account every single observation, right? And adds them together. Does the median do that? Not really, right? The median just looks at what falls in the middle. So the median doesn't care if your lowest grade was a 62 or a 22, right? Let's say your lowest grade was a 22. What would happen to the median? Nothing, right? It would still be 90. But what's going to happen to your mean? Well, it's going to get pulled down even more, right? So that's the difference in the mean and the median. So what we're going to look at is if we notice that we have really low observations or some really high observations, then we have to be aware of the fact that the mean is going to be affected by those high or low numbers, okay? And in that case, it might make more sense to use the median instead of the mean, okay? Now, a term we're going to talk about here is resistant, okay? A numerical summary, so that means a statistic or a parameter, is said to be resistant if extreme values, so very large values or very small values, these are also called outliers. I'm not very good writing with this, but okay, so outliers are also what we can call extreme values. Do not affect its value substantially. Okay, so if we have really high or really low values and they don't really affect our statistic or our parameter, then we say that that statistic or parameter is resistant. The median is resistant, okay? Because like I said here, if I change this to 22, which would be considered an outlier because it's much lower than the rest of the data, then the median doesn't change. So it was resistant to that low number. But the mean would change, right? So it is not resistant to those really low numbers or really high numbers, okay? So because of that, because the median is resistant and the mean is not, if we do not have a symmetric distribution, so a distribution where most of our data is in the center and there aren't any high or low outliers, then we want to use the median instead of the mean. Okay, so for skewed distributions that would look like this or this, where we have some low extreme values, so low outliers, or high extreme values, so high outliers, the mean is going to follow those extremes, okay? And what that does is, even though we calculated the mean correctly, the mean doesn't really accurately represent the data because what it's done is instead of looking at, you know, where most of the data is, it's being pulled down or pulled up by those extreme observations, okay? And so we would rather use the median in those cases because the median is going to give us a better description of our data. Okay, so these are the general rules. If your distribution is skewed, so it looks like this or this, then use the median, okay, because it's not as affected by outliers. If your data is symmetric, so it looks like this, then the mean and the median should be fairly similar. So either of them will work, but we'll probably just use the mean mainly because when you're talking to most people, they understand what a mean is. But if you tell them the median, you may have to explain it a little bit. So if we can go with the mean, we would like to use the mean. But there's going to be some situations where it just makes more sense to use the median to describe our data. So let's look at an example here, just to kind of remind ourselves again about how that outlier is going to affect our statistics. So find the mean and median of the following set of data. It's already in order here. To find the mean, we add them all together, divide by n, and we get 19. To find the median, we could do n plus 1 over 2. There's 6 observations here, so 6 plus 1 over 2 gives us 7 over 2, which is 3.5. Is 3.5 our median? No, right? 3.5 is telling us where our median is. Okay, so since it has a 0.5, that means it's between 3 and 4. Okay, so it's between the third observation and the fourth observation. So we go up here to our numbers and we say, okay, this is the third, this is the fourth, so our median falls right in between there. We add the two together and divide by 2 and get 18.5. So that's the number that would fall right in the middle of those two numbers. Okay, so that's our median. So the mean is 19, the median is 18.5. So those are both fairly close. So if we have means and medians that are pretty close to each other, then that lets us know that our data is probably pretty symmetric. Okay, so it means that there's probably not many high or low values. And we see in this data set, that's what we see happening, right? There's not any numbers that are much lower than the rest of the data or much higher, okay? But now let's say we change the 30 here to a 50. What's going to happen to our statistics? Well, the median we know isn't going to change, right? Whether that's a 30 or a 50 or a 1,000, whatever it is, right? Our median is still going to be right there in the middle. So our median will still be 18.5. But our mean is going to be affected, right? Now the sum of the numbers is going to be 134. We divide that by 6 and we get 22.3. So you see our mean has increased because we changed that one number, okay? And so now the mean is higher than the median, which means we're looking more at a distribution like this, where most of our data falls down here, but we have this one high outlier over here of 50, right? So that's what we're looking at here, showing how changing that one number makes a difference with your mean and your median. So how would this apply to real life, using real data? Well, let's think about income in the U.S. Okay, the government is trying to present information about the average salary in America and whether it's increased or decreased in the past 2 years. What would be a better way to describe the salaries of Americans? Would a median or a mean be a better representation? Okay, so we're looking at, this is real data. This is from basically the last census, is where the most accurate data is, even though that was in 2010, but that was our last census, so we actually have parameter data there. So we're looking at this, and this is how income typically looks, okay? So we have a large amount of people that are down here. So from making basically nothing up to maybe 100,000, right? That's where the majority of our people are. And then we have very few that make more than that. And you can see, we have a few people out here making millions and billions of dollars, right? This says 250,000 and over. So you know, that whole group there contains people that make 250 all the way up to, Bill Gates and all those kind of people that are making millions and billions of dollars. Okay, so they also fall in that category, which might be why it's a little higher there. If we actually extended this forever, and had more categories out here, these would probably just keep getting smaller and smaller and smaller, right? But we can very easily see that this takes on that right skewed shape, okay? Because most of the data is small, but few of the data is high or large, okay? So what happens here is the median happens to be around $50,000. The mean, though, is at about $59,000. Now, it doesn't say it here, but I got that from some other information about this data, okay? So the mean is about $59,000. So we can see that the mean is being pulled up by those higher numbers up here. So what would be a better representation of our data? Would it be better for the government to tell us what the median is or what the mean is? Well, they might want to tell us the mean, right? Because the mean is going to make it look like things are maybe better than they really are. And let's say the next year the mean goes up to 70,000. Well, does that mean that most of us have seen a pay increase? Or does that just mean that we have more millionaires and billionaires? Well, it could mean that we just have more millionaires and billionaires, right, that are pulling that mean up. But if the median was to increase, that's telling us that the middle of the distribution actually moved up, which means that this whole thing is shifting over. Okay, so we would rather hear about the median because the median is going to represent this data better. The next one says a report states that a new diet produced an average weight loss of 35 pounds after 6 months in a study of 100 participants. When you look closer at the study, you notice that most participants lost 5 to 10 pounds, while one participant lost 67 pounds. What is the mean and accurate representation of the data? Okay, so if we were to draw this out on a histogram, we're saying most people lost down here at like, sorry, this is a terrible graph, but they lost down here, let's say this starts at 0, and 5 pounds, 10 pounds, 15 pounds. So most are losing this amount over here, right, in our histogram. Then we have one person way over here that lost 67 pounds, okay, way over there. So what has that created? Well, it's created that long right tail, which is a right skew distribution, okay? So what happens to the mean when we do that? Well, the mean gets pulled higher, okay? So if this is the average weight loss, does that mean that's what you should expect to lose? Well, not really, right? Because most of the participants did not lose that. One person lost a whole lot, and that has skewed that average, okay? So it would be better if they gave us the median, because the median would probably be somewhere down here, let's say around 10 pounds or something. And that median would better describe the results you should expect. Okay, so the median would be the better representation. All right, the last one here, you want to find the average weight of pumpkins sold at the farmer's market. Would it be acceptable to use the mean? Well, how do you think the weight of pumpkins is going to look? Well, if you don't know, then it's probably just going to be symmetric. I mean, if you don't have any reason to believe that if we don't have a farmer that's also bringing his giant pumpkin from the state fair or something in, we're going to expect that probably most of the pumpkins from this farm are going to be, let's say, I don't even know the weight of pumpkins. I just guess. Let's say they're mainly about 4 pounds. Then you have some at 3, a few at 2, okay, and then you have some at 5. Some at 6, whatever. So, but in general, probably most of them are going to be around the same weight because they've grown in the same fields, they were watered the same, fertilized the same, etc., right? Had the same climate and all that. So we're expecting probably most of them are going to be about the same. So it would be fine to use the mean. There's no reason to believe that it is skewed either way. Okay, so as long as you can't find a reason to think there would be any skewness in your data, then you're fine to use the mean. Okay, it's only when there's skewness that then we get a little concerned that maybe the mean is not a good representation of our data. Okay, so that is the end of 12.2, and I'm just going to end there, and I'll do another video for 12.3, which is where we start talking about how our data is dispersed. So now we know where the center is. Next, we're going to talk about how spread out is our data. Is it really close to the mean? Is it really spread out from the mean? And how do we judge that and how do we calculate that? So that will be what I talk about next time. If you have any questions, remember you can email me at angela.galloway@kctcs.edu.